This is the first of a sequence of 2 videos to demonstrate what I think is the most important concept of inferential statistics, that is the central limit theorem, and how you can use the central limit theorem and sampling distributions to make inferences about a population. In our Excel spreadsheet here, I have a function or a command that randomly generates values of a variable, and I'll see I can get that value to change randomly. And then down at the bottom, I have a Excel command built in to count the number of data points that I'm looking at. Currently I have 1. I can certainly change that. Now I have 2. And it also calculates the mean of whatever values of that variable I have created. Now currently I have Excel set up to randomly generate values that are exactly normally distributed. They come from the normal distribution. And I've preset the mean of that distribution to be 40 and the standard deviation to be 10. Now we know from the empirical rule that 68% of values should be within 1 standard deviation of the mean of 40. And as we randomly generate these values, you'll see that about 68% of the time, about 2/3, a little more, values are within 1 standard deviation, that is between 30 and 50. And about 95% of the time, the values are within 2 standard deviations, between 20 and 60. And nearly all of the time, about 99.7% of the time, the values are within 3 standard deviations, and that would be between 10 and 70. So 3 out of 1,000 values are going to be either below 10 or above 70, and so far I haven't seen any of those, and I'm certainly not going to try this 300 times to see if we can find one of them. But it is possible. Now, the concept of a sampling distribution is illustrated if we expand our sample size to n equals 4, and we look at the behavior not of the 4 values themselves, which we know come from a known distribution with a mean of 40 and a standard deviation 10, because I designed it that way, but we look at the behavior of the mean of those 4 values. That is, we look at the behavior of x bar. So as I randomly generate those 4 values in my sample, we see that sometimes x bar is above 40, sometimes it's below 40, and on average, it is exactly 40. If you don't believe me, you'll just have to trust me. The textbook agrees. However, as we're watching those values of x bar, you might notice that very, very rarely our value is less than 30 or greater than 50. Remember, a single value of x is between 30 and 50 68% of the time. But as I've randomly generated these values, I haven't seen a single value of x bar that is beyond 30 to 50. Now, the reason for this is to get a value of x bar that's, say, significantly low, maybe 25, I would need a value of x up here that is significantly below the average, say 20. And I would need another value of x that is significantly below the average of 40, maybe 28. And another value of x, like 24, and another value like 27. And while values like that can certainly happen, it's very rare to get 4 of them randomly chosen, all significantly below the true mean of 40. That would result in a value of x bar being something like 25. It's much more likely that while I might get some values that are fairly small, in fact I might even get 2 values that are fairly small, it's also likely that I'm going to get a couple of values that are significantly above 40, so that the average of those 4, or 1 value of x bar, is very close to the true average of 40. Our observation that extreme values of x bar, like 25, or substantially above 40, maybe 55 or 60, are much less common, tells us that the standard deviation, or the dispersion of x bar, is much lower than the standard deviation or the dispersion of individual values of x. That is, if I were to plot many, many, many values of these x bars on, say, a histogram, the standard deviation of those is going to be less than 10, even though the standard deviation of individual values is exactly 10 by design. Now we can see this further by increasing our sample to, say, 16. Again, individual values of x could be above 40 or below 40. We see we've got a 22, a 31, a 22, a couple more in the 30s, and then a couple more in the mid to upper 40s, and a couple values in the 50s. Again, about 68% of the values should be within 30 and 50. 95% of them, and in fact in our sample we have all of them, are between 20 and 60. But watch the behavior of x bar as I regenerate these values. Some values are below 40, some values are above 40, but very, very rarely are these values of x bar significantly far away from 40. In fact, we haven't found, well, there's a 39. We haven't found any values that are below about 33 or so. And we haven't found any values that are above about, we'll say, 47. So again, we see that while individual values of x have a standard deviation of 10, and 68% of the time they're between 30 and 50, the values of x bar, about 68% of the time, they seem to be within maybe 37 and 43. It's a much smaller range. And we can continue this one step further. Let's say increase our sample size to 36, and there's a reason I picked those numbers. So far we've looked at a sample size of 4, 16, and 36. Now think of how unlikely it would be to get a value of x bar of, say, 45. You would need one value of x of, say, 45, maybe 47, another value that's maybe 42, another value that's maybe 50, another value that's 40, and if you ever get a value of, say, 30, which isn't all that uncommon, you would need a value something like 65 to offset that so that you can get your sample mean to be something like 45. That's pretty uncommon with this many data points. And we'll see that these values of x bar are never that large. 37, 41, 39. Nearly all of these values of x bar are between about 36 and 44. And I'd say that about 68% of the time they're probably between about 38 and 42. So again, we find that as our sample size is much larger, it's very uncommon to see values of x bar that are significantly above or below the true mean of 40. Now, the concept of a sampling distribution is that distribution of all the possible values of x bar. What we found in this little exercise is that if we know that the mean of an individual variable is 40, and we know that the standard deviation of these individual values is 10, we know that the mean of all possible values of x bar, that is the population of all possible sample means, still has a mean of exactly 40. It has the same mean as the distribution of individual values of x. We've also found that the standard deviation of x bars, or the dispersion, is much smaller. The formula in the textbook says that the standard deviation of x bars is equal to the standard deviation of the original values of x, in my example it's 10, divided by the square root of the sample size. It's for that reason that I chose sample sizes of 4, 16, and 36. When our sample size was 36, as it is here, the standard deviation of these x bars is 10, the original standard deviation, divided by the square root of 36, which is 6. So the standard deviation of this is 10 divided by 6, which is 1.67. So 68% of the time, these values of x bar are 40 plus or minus 1.67. That would be 38.33 up to 41.67. 95% of the time, those values of x bar should be within 2 standard deviations of x bar. That would be 3.33 above or below 40. So 36.67 or 43.33. That means that only 5% of the time are these values of x bar going to be either below 36.33, sorry, 36.66, or above 43.33. And indeed, we find that values that far away from 40 are pretty uncommon. Now, working backwards, maybe we'll do a sample size of 25. So now the distribution of x bar can be a little bit more spread out. It's a little bit more likely to get values of x bar of, say, 36, 37, or 43, or 44. And the standard deviation of all possible values of x bar, when we look at 25 observations at a time, is 10 divided by the square root of 25, which would be 2. 95% of the time, these values of x bar are going to be within 2 standard deviations of 40. That is between 36 and 44. And if we shrink our sample back down to 4, we know that the standard deviation of x bar is 10 divided by the square root of 4, which is 2. So while individual observations of x have a standard deviation of 10, and 95% of the time they'll be between 20 and 60 within 2 standard deviations of 40, these values of x bar have a standard deviation of only 5, and so 95% of the time those values of x bar are going to be within 2 standard deviations of x bar, and that would be between 30 and 50. So one more time, we see that the distribution or the spread or the dispersion of x bar is smaller than the distribution of x. Now, in the next video that accompanies this one, we're going to see how you can use that principle of sampling distributions, that is the distribution of sample means, here we go, to make inferences about a population when you don't know the mean and the standard deviation to begin with. And that's the principle of confidence intervals and hypothesis testing.